again, our most valued student. My name is Confident. Welcome to our revision session of the Engineering Science N2 paper, which was written in August 2021. Now, in this particular lesson, we are looking at the last part of the paper, which is the last three questions. The first three questions was question 1, 2, 3. Then that was part 1. We went to part 2, which looked at question 4, 5, and 6. And in this section, we're looking at question 7 up to 9. As I said, this is the Engineering Science N2 paper. Now, if it happens that you are seeing this video for the first time and you haven't seen part 1 and part 2, chances are this is your first time watching this channel, and therefore I will encourage you to, first of all, I would like to greet you and welcome you into the 24-minute lesson where we look at mathematics and engineering science. We also look at the grades in terms of those who are doing grade 7 up to grade 12. And we are also looking at the N1 up to N4 in math and science. Now, if you have not subscribed to our channel, I'll encourage you to subscribe to our channel, as well as make sure that you turn on that notification bell so that you can be notified every time we post some new videos. So now, in this particular, as I said, in this particular lesson, I'm looking at part 2 of this paper, which was written in August 20, part 3 of this paper, which was written in August 2021. Now, we've looked at the introduction in terms of going through the formula sheets and everything. As I said, you need to grab hold of that. But now I'll go straight into question 7. So we just did question 6 in the last lesson, which was on friction. So the first question that I'm interested in is question number 7. So let us look at this question, and the topic or the module that it is focusing on, it is the module on heat. Now, if you look at this question, let's look at question 7.1. It says, give one example where linear expansion of metals is useful in practice. So in other ways, what is the practical use where you find linear expansion? And when we are talking about expansion of metals, now think of things like the kettle in the house that is used to boil the water. Think of things like the stove that makes use of linear expansion, the iron that you use for ironing your clothes, and the most important metal there, we call that the bimetallic strip. The bimetallic strip. So this is one area where you find an example of the linear expansion. So this is the bimetallic strip that you find in thermostats. So that is the first one that quickly comes in mind. If I can just try to think of the other part, but mainly nothing is coming as such, but you need to find other examples. But the main part of linear expansion of metals, remember they are specific about metals, is whereby you are using the bimetallic strip. Another one that is coming in is the mercury in a thermometer, but this one I will encourage you to check it out, the mercury, because mercury is a metal, so the expansion of mercury for measuring temperature. But the one that I'm saying, the linear expansion that is most common, as I said, it is the bimetallic strip. So that is one mark, so that's why I'm not focusing much on that, but find some more examples where linear expansion is used. 7.2, it says the length of a metal bar at 26 degrees was found to be 5 meters. After being heated to 89 degrees, the bar expanded by 7,245 millimeters. So let me just read this. Let me just remove the first part so that we can focus on the second question. It says the length of a metal bar. So we're looking at the length of a metal bar at 26 degrees was found to be 5 meters. So now this particular length, which is L, of a metal bar at 26 degrees, this is temperature. So we can call this one in a way, this is my T1, was found to be 5 meters. So this is my initial length, which is my L0. After being heated to 89 degrees, so this is my T2, the bar expanded by 7,45. So this is my change in length. So now where am I getting to? The question is identify the metal bar. So it says we need to identify what type of metal it is. And then it says an answer without calculation will not be accepted. So if you just guess and come up with the right answer, they are not going to give you any mark. So you need to calculate. So if we go to our formulas and see which formula is most applicable, and remember we're talking about linear expansion, and the formula that you need to use for linear expansion is this particular formula here, which is change, as you can see, change in L is initial length of the metal times the coefficient of expansion times the change in temperature. So if I can use this formula and write it to say, I'm just going to work it here to say the change in length is equal to L0, and then multiply, they use the dot, times that alpha sign, the coefficient of expansion, and then times, we're looking at the change in temperature. So now if you rewrite this, you're going to say change in L is equal to L0 times that alpha times, and then is the final temperature T2 minus the initial temperature, which is T1. So now we input the information that we're given. First things first, you see that we are given here 7,2. So we have got 7,245 millimeters. You need to convert this into meters. So you say 7,245 divided by 1,000. Are you with me? Because the SI unit of length for length is in meters, so it's 7,245. It is good that you divide it by 1,000 already so that you can get that. So it is 7,245 times 10 to the power negative 3. Now you can actually change that into a decimal, and then you say shift, then you say fix, which is 6, and then up to 9 decimal places it can give you the actual number, which is 0,007245. So it's 0,00745. Now this is in meters. Remember, after converting, this is changing into meters. So now if I'm going to input the values that I'm given here, already 5L's initial length is in meters. So the change in length, which is my 0,007, and then we have got 245 is equal to my initial length is 5 meters times, we don't have the alpha, the coefficient of expansion, and then we have T2, which is 89 minus T1, which is 26. So now if I simplify this, just to make it easier, I just want to show you how you can just make this thing much easier to simplify. Remember, now I need to make alpha the subject of the formula. So what I need to do is to just remain with alpha so that I don't complicate things. This is now math. So I'm going to divide both sides by what is not alpha. Remember, opposite of multiplication is division. So I don't need that 5. I'll divide by 5. I don't need this bracket 89 minus 26. Those are the things that I don't need, so I can see that cancels, and I can cancel that, and I can cancel that. But remember, what you do on the left, you must also do on the right, which is 589 minus 26. So I just wanted to show you how simple you can do that. So now if I'm going to then use my calculator, I'm going to have 0,007245 over 5 times 89 minus 26. It is going to give me a big number, which is 2,3 times 10 to the power negative 5. So now if I can do the same part whereby I am saying shift setup, I change to fix, which is 6 there, and then to 9 decimal places, I'm going to get 0,0000. So there are how many zeros before the number? It's 1, 2, 3, 4. So 0,4 zeros and 23 0. So it's 4 zeros. So the answer is 0, so there are 4 zeros. 1, 2, 3, 4, 23 0 is equal to, this is, remember, I'm looking at the coefficient of friction, which is in this case per degree. This is over degrees per degree Celsius is equal to alpha. So that is my alpha. Now the question is, I need to identify what type of metal is this. So what I'm going to do then is to go to my constants here, and it is where I'm going to look for the linear coefficient of expansion, and you can look at the numbers. Remember the number that I got this number 0,00023 per degree. So if I come here and look at the numbers, you can see there is the number that I'm getting there. So it's got 4 zeros, 1, 2, 3, 1, 2, 3, 4, 23 per degree, and you can see that it is the linear coefficient of expansion of aluminium. So this is the key part, aluminium. Now the question says here, I need to identify the metal. So after this I say, therefore the metal is aluminium. So that is how you can use the calculation to help you to identify the metal. So that is how you can get the 3 marks in that. Now let us look at question 7.3. Now 7.3 was based mainly on definitions. It says, and that is an emphasis to say, throughout the whole paper, if you check properly, 20% to 25% is just definitions, sometimes even more. So if you can also focus on your definitions, you can literally pass your paper just by fully knowing your definitions, meaning if you take them lightly, they can cost you a lot in your exam. Now let us look at question 7.3 now. Question 7.3, it says, explain what is meant by each of the following terms with regard to the heat content of water. So water is the kind of the guide in these definitions. The first one is 7.3.1, the specific heat capacity. What is the specific heat capacity? 7.3.2, what is the latent heat of evaporation? 7.3.3, what is the sensible heat? So this, you are getting 2 marks each to a total of 6. So I just provided them in a simpler way so that you can look at them. The first one is the specific heat capacity. What is it? It is the amount of heat energy required to raise the temperature of 1 kilogram of water by 1 degree Celsius or by 1 Kelvin. So that K there is the Kelvin. So it's the amount of heat energy required to raise the temperature of 1 kilogram of water by 1 degree Celsius or by 1 Kelvin. And then the latent heat of evaporation, it is the heat which causes no change in temperature. So whenever you're heating something and the temperature is not changing, like especially in the case of, let's say you're melting your ice, the temperature won't change until all the ice has melted. So that is the latent heat of evaporation. I mean the latent heat. Now the latent heat of evaporation is when you're heating the water, there won't be any temperature change until all the water has changed from liquid to gas, that is steam. So we're saying that heat is the heat which causes no change in temperature, or it is the heat during change of phase between water and steam. So that latent heat, that is the latent heat of evaporation. Now the last one is the sensible heat. In this case, the sensible heat is the heat causing rise in temperature applicable to a single phase, which may be ice, water, or dry steam. So that is the heat that is causing rise in temperature. So it's called the sensible heat. So guys, as I said, definitions are very, very important for you to master. So if you don't take them lightly, they can cost you much in exam. Now let us move on to the next part. Now we are looking at question number 8. And question number 8 in this instance, it focuses, if you look at question number 8, it is the chemistry side of this paper. It's just a small section where it deals with chemistry. So let us look at that part of the paper, and we are looking at the particle structure of matter. Now the first part of the question, it says here 8.1 says we must define an element. So now usually it's an old definition that is always common. An element. What is an element? Remember, an atom is the smallest particle of an element. Now what is that element? An element, it is a group of atoms. It's a group of atoms of the same kind in a substance. I'm putting it in bracket. An element is a group of atoms in a substance. In a substance. So an element is a group of atoms in a substance of the same kind. That's the key word there. It must be the same type or kind. So remember, I said an atom is the smallest particle of an element, but that particular element, if you group same atoms together, you get a substance, and that particular substance is an element. So you get 2 marks for that. Now the next part, 8.2, says give 2 examples of an element. This is so wide open. There are many examples. Just focus on the periodic table. All those elements, they are, actually I just said the word, all those names in the periodic table, those are elements. The elements of the periodic table, you can name it. You have copper, you have sodium, anything. You have got aluminium, just any, guys, any aluminium. You have got zinc, anything. It was an open question, so there is no one answer. Anything, as long as it is the element of the periodic table there, that is an element. So copper contains only copper atoms, sodium contains only sodium atoms, and it can be magnesium, contain only magnesium, oxygen contains only oxygen atoms, chlorine contains only chlorine atoms. So those are elements. All right, so let us move on to the next question. So that was more like a continuation of 8.1, 8.2. 8.3, it says give 2 examples again of compounds used in households. Again, it is an open question, but you don't need to think too much. There are always 2 common compounds used in the household. This question, they like asking it, but when they ask you this question, don't let your mind wander too much and then you're like, what compound are they talking about? There are 2 simple compounds that you use every day at home. That's why they say it in the household. The first one is H2O. That's a compound, you see, where you combine hydrogen and oxygen. So the first compound is water. You like to say H2O, give me H2O. The next compound, you use it when you're eating. It is sodium chloride, which is salt or table salt. But it's good to call it by name and say sodium chloride, because if you say table salt, that's not its actual name. The actual name is sodium chloride. And then so you don't write table salt but write sodium chloride, and then you can come up with a little more. They say it's 2 marks, they say 2, but you can add now some like vinegar. Now the vinegar, you can get your mark by saying vinegar, but this one, it's your CH3COOH, which is the acetic. This is acetic acid. Okay, and then when you are baking, remember the bicarbonate of soda, that is another one, bicarbonate of soda. That is your baking powder, this one. So anything that is a compound, anything, as long as you will know its chemical name, like bicarbonate of soda, your vinegar, which is the acetic acid, but I think they will give you, even if you say vinegar, vinegar is the trade name, acetic acid is the actual naming of that compound. So that is that. You get 2 marks for that. So these are just simple examples that you always use to take care in chemistry. They are such simple questions, but they can cost you marks. So already you say this is 6 marks, and the last 2 marks is name 2 types of ions. Now the ions, if you remember, they are positive ions and they are negative ions. So the first type, as you can see, it's positive ions, but they have a special name. We call them cations. Alright, so the word they wanted there was cations, but even if you say positive ions, is correct. Now you still remember now the negative ions. So don't just leave the signs like that, they'll penalize you. So you say negative ions, and these are the anions. The word that they actually, that's why they say name 2 types of ions, the cations and anions. But if you say negative ions, they will also mark you correct. So that is what will give you a last 2 marks of the 8 marks. So that was it on the chemistry section. Lastly, let us look at question number 9. Now, question number 9 focuses on the module on electricity, and with that, we're going to wrap up this paper. As you can see now, the paper is out of 100, but let us look at this question. It's also one of the sections that has got some marks. The first part is when we're looking at the chemistry section here. The first question says, what is the relationship? As you can see, that's 9.1. What is the relationship between current and resistance? So they wanted to ask the relationship there. But now, if you still remember, you have that kind of a triangle which says resistance is equal to voltage over current. Remember this kind of triangle where you have R, V, and I. So now they are asking you, what is the relationship between current and resistance? You can actually use this formula. If I go to my formulas here, and okay, all right, they didn't bring that, the Ohm's law, but if you still remember, the Ohm's law formula is actually this one, which says resistance is equal to voltage over current. So now the question is, what is the relationship between current and resistance? So now, if I can ignore this part here, V, and I put a 1 there, you can see that V is equal to 1 over I, meaning the two have got an inverse relationship. So what is the relationship? We can say in this relationship, current is inversely, let's start with resistance, since we've got R is equal to, we can say resistance is inversely, that 1 over means it is inversely, that's the word they are looking for, So resistance is inversely proportional. That's a proportion. Proportional to current. So that's what they wanted you to say. To say resistance is inversely proportional to current. In maths, you can write it like this. R is not equal to, actually, you're going to say R is proportional to 1 over I. That is the statement. Resistance is inversely proportional to current. Or you can make it simple, like in layman's language. You can say as the resistance increases, the current decreases. Or you can say resistance and current are indirectly proportional. Or when current increases, resistance decreases, and when resistance decreases, current increases. Anything that shows that when one goes up, the other one goes down. That's what they wanted to pick up there. So resistance is indirectly proportional to current or inversely proportional to current. That is 9.1. And then we move on to 9.2. In this case, says name 3 disadvantages of induction. Remember, when you're inducing current, so what are the disadvantages of induction? Number 1, if you still remember, this is one of the most common questions that they usually ask on the disadvantages of induction. It causes the brushes to spark. So meaning you have to replace the batteries time and again. So it causes the brushes to spark, so leading to worn out brushes that makes you replace these brushes. And then the next one is the eddy currents that causes heat, loss of heat, and that is a loss. Eddy currents causes heat, and that heat is undesirable. Okay, they said three of them. And then let me think of the other one. It can also affect other apparatus. Say when it malfunctions, it can affect other electrical gadgets. So malfunction can damage other devices. So if it malfunctions, it can damage other devices also. Other devices, which is a disadvantage in this case. And then maybe number 4, again based from that part, to say it is prone to lightning attacks. Because it usually conducts lightning. So these are the 4. Just go through your book. I think it's something that you always find in the books, that if you just say disadvantages of induction, you can just get. Please, it's an important question that you need to master, so that by the time you are sitting for your exam, you are well prepared for that. Now let us look at 9.3. And in question 9.3, it says a simple DC circuit has a supply voltage of 12 volts and a resistor R1 of 3 ohms is connected in series with the supply. The resistor is connected in series with 2 resistors R2 and R3 connected in parallel to each other. Calculate the following. So if I'm going to be able to calculate this, I think I need to be able to draw this first. So let me sketch this. What am I having? I have, in this case, a 12 volt supply like that. Remember, so when I'm having like this, so remember, this is my positive, this is my negative. So what I have here, okay, I'm gonna ignore the switch. So what I have, the first thing I have is, they said a 12 volt voltage supply. So in here like that, if I can, let me just erase this for now. If I can come here and say, this is what makes it to become, for me to able to measure this V here is my 12 voltage supply. You see that? So that is across the battery. So a simple DC direct circuit has a supply voltage of 12 volts and a resistor R1 equal to 3 ohms is connected in series with the supply. So how do I present that? They are saying a 3 ohm is connected in series with the supply. There are many ways. I can put it there like that. There is the series. But now to avoid that, and then they're saying it is in parallel though. It is, the resistor is in series with two resistors, these two in parallel. So I can then move on to do this. But I'm going to change this. I'm just trying to show you the different variables that I could have done there. Then these two are like this. See that? Like that. So this is how this whole part was going to come out at the end. So this is what I'm looking at. So it's in series and parallel with that. But now, just to simplify it for me, I would prefer it to be like this. As I say, there are different ways you could have done it. Yours is also correct. So here I want to put my first resistor there like this. I'm going to put this first resistor like that, and then from there I'm going to then have my parallel combination there like this. See what I'm doing there? I just wanted them to be clearly in this kind of perspective like that. So, and then these come like this, and you can then move on to join them like that. It's up to you how you want to join them, but this is how I wanted this thing to be. So now let me label again. They say R1 is 3 ohms, so this is my R1 equal to 3 ohms, and then they say this resistor is connected in series with two resistors R1 and R3 connected in parallel. So we have got R2, which is 6, and I have got R3, which is 4. So I sing that. So this is how the diagram was. Sometimes they'll say sketch the diagram, but in this case they were very, in a way, stingy not to give you the marks for the diagram. But you need to have a visual picture of this diagram for you to be able to calculate. Now let us look at this. The first one is 9.3.1. Calculate the effective resistance of the circuit. So we need to find, in other words, the total resistance of the circuit. So here we are focusing on that section of the part. You are adding those resistors. Now if you go to your formulas, your formula has two types of resistors. This is resistors in parallel, which is given that, or RP sometimes given that, and then resistors in series, which is RS. So I'm going to use those two formulas here. So for the first one, which is resistors in parallel, remember that formula for resistors in parallel says, it says 1 over RP. See that one? So I'm using this formula 1 over RP. So if I use it here, I'm looking at the two resistors in parallel. So I'm adding that and that. That's what I need to do first. Deal with the parallel combination, which is 1 over RP is equal to 1 over 6 plus 1 over 4. Now 1 over RP, if I simplify that, it will, with the calculator, I'll say rely on the calculator please. It's 1 over 6 plus 1 over 4 which is equal to 5 over 12. So I've got this as 5 over 12. Now, most students always say RP is 5 over 12. No, that is not the answer. Remember, for you now to find the answer, you have to flip. In other ways, RP goes to the top and 12 also goes to the top, and the number 5 goes to the bottom, and this number 1 goes to the bottom. So in other ways, I'm saying RP goes to the top, not RT, but RP. You just flip them. RP over 1 is equal to 12 over 5. You just flip them like that. So it gives you now your RP, which is RP is equal to 12 over 5. And you can find now what is 12 divided by 5, which is 2,4. Remember, resistance is measured in ohms. So that is the parallel combination. And the last one we need to now add. So this is now in series. So what you'll be having, that part at the bottom, so it's like I'm having this now. This is what I'm having. Here I've got the 3 ohm, and then here I've got the one I was adding, which is now my 2,4. So you see how it's like now. This is what I'm having now. So I've got series now, which is my RS is equal to 3 plus 2,4, which is equal to 5,4 ohms. No, I know it's simpler like that, but just to verify, 3 plus 2,4. You know, it's always good to check. It's 5,4 ohms. So that is the effective resistance. And then we can come here. I hope you saw how I worked that. So I'm going to erase here so that I can write it in front of this. So effective resistance is equal to 5,4 ohms. Are you getting that? Now let's move on. 9.3.2. I have to erase this now. 9.3.2. It says the total current flowing through the circuit. Now, to find the total current flowing through the circuit is an open question, but still remember what I did. I showed you this triangle like that previously when we're looking at the Ohm's law. And in this triangle, what does it say? It says a resistance is a voltage over current. You need to remember this triangle. So now the question is, it wants me to find the current. So I'm looking at I. So I is equal to V, and then there's over. See that part? It means over V over R. You seeing that? Therefore, I is equal to, I'm given my V, which you saw that it was 12 voltage. Say it is the DC is a supply voltage of 12. So my V there is 12 over R is the total or the effective resistance that we just calculated, which is 5,4. It will give us the current that is flowing through this whole circuit in amps. So if I use that, it is 12 over 5,4, and then it gives me 2,2222. So you can see that it is in a way, if you round off to 3 decimal places, it will be 2,222. So if I write that, it is 2,222. Now remember, I'm dealing with current, so the units are in A for amps. So that is that part, and it can then you can use that then to simplify. So that was the simpler way you could have done that question. It's just 2 marks, so don't overthink it. Always use the formula. Current is a voltage over resistance, and this triangle, just try to get common or familiar with the triangle. So if I write that question there for I is equal to 2,222 amps. All right, So now I can erase this part. Last question, I'll just leave that triangle for the time being. Says 9.3.3, the current flowing through the 6 ohm resistor. So they want the current is 3 max, so it needs a little bit of thinking, but it's interested in the current that is flowing through the 6 ohm resistor. Now it's an open question. You can do it in different forms. I'll show you maybe 2 different ways that I usually approach it, but let me just work on it from this perspective. Now remember what we did is we drew this diagram previously. After when we're calculating the effective resistance, we said this was my R1, which was 3, and I got the total resistance of that, which was what was this parallel, I think it was 2,4. Let me just quickly do the calculator. Remember, when we're adding the parallel side, the 1/6 plus a 1/4, just to get that number, 1/6 plus that 1/4. When we're adding the total, it was 5/12, and then we said you invert to say it's 12/5, like that, and then I think it was 2,4. All right, now I remember. So we had 2,4 ohms. Now this is the total of the parallel combination. Now what happens with resistors in series, you need to know something, is that when I connect my voltmeter here, my V, like this, and I connect another voltmeter, I'll call it V1, okay, V for 3, let's use V3, meaning voltmeter in the 3 ohm, as well as if I connect this voltmeter in the 2,4. So these voltmeters, when I add this V3 plus the V2,4, I must get the total voltage. Remember, I've got the total voltage, which is 12 here. You understand? So I get 12 volts. Now where am I getting that? Let me check if the formulas also do give us that part of voltage for the resistors in series and parallel. Alright, there is no formula, but remember that. And at the same time, when I come here to the voltmeters in parallel, if I connect a voltmeter here, and if I connect a voltmeter here, the reading of V6, the voltmeter 6, must be equal to the reading on voltmeter. I'll call it voltmeter 2 actually, because they used R2. So the reading on voltmeter 2, that is from R2, must be equal to the reading on voltmeter 3, which is R3. So voltmeters in parallel are the same, or voltage in parallel resistors is the same, and voltage in the series resistors, you add them so that it can equal the total voltage of the circuit. I can use that information to calculate. So what am I trying to say? I'm saying we know what is the current here. You see, the current here we just calculated. We said the current was 2,222. So that is the current that entered. That is the current that entered. So we know what is the current that entered. And the question is interested in the 6 ohm. You see that? So because they're interested in the 6 ohm, and the 6 ohm is linked to the 2,4, so I'm going to find the voltage there. So how do I calculate it? I use my triangle. V is R times I. Remember that? So, or IR. So I'll use that formula to say V is equal to I times R. Now I know my current, which is 2,2, times my resistance, the total resistance of the parallel part, which is 2,4. If I multiply that, it is going to give me in this scenario 2,222 times 2,4. It is giving me in this case 5,33. It's 5,333. So that is the voltage. So V is equal to 5,333. So what is that? It's 5,33 volts. Now the question, though they're interested in the current, remember, they want to find the current that is passing only in the 6 ohm resistor. But now I found the voltage. The voltage that is passing here is 5,33. The voltage that is passing here is 5,333 and 3. So that is what is needed. Now I can therefore find the current. Look at this. Now when current comes here, it is going to divide. Some of it will go this direction, some of it will go that direction. So I'll call this I2 and then I'll call this current I3. So we are interested in the current I2. Now using the formula for current, I is V over R. So I use that formula as I is equal to V over R, over R. So I is equal to my voltage. I just calculated it, which is 5,333. Now it's V for 2. It's just V, but for R, let's use 2 because I'm focusing on R2 over 6. Then it will give me the current that is passing through. If I do that, I will say 5,333 divided by 6. Press SD, it is 0,888. So 0,888, that is 0,889. So I've got 0,889 in current is in amps. So that is the answer. That is the current. That is I2. Therefore you can say current flowing through the 6 ohm resistor in this case is equal to 0,889 amps. But just if we test if ever our question is correct, let me find the current that is passing through the R3. It's the same form. I3 is equal to V over R3. But I was not required to calculate that, but I just want to show you something. The V is still the same, which is 5,333. Remember, this is a parallel combination, so the voltage is the same, but what is different is the resistance, which is 4. So my I3 is equal to, if I calculate that, which is 5,333 divided by 4, and it's 1,333. So I'll get 1,333. This is amps. Now you see the current that is flowing through I2 and I3. If I add it, just to show you something here, if I say I2 plus I3, I must get the current that entered through here, and we know that current, we calculated that particular current. That was the question that we got to say the current was 2,222. The current that was flowing here was 2,222. Even here, before it split, it was 2,222. So let me add my I2, which is 0,889 plus 1,333. If I add that, it must be in a position to give me the current that is passing, that entered before it split. 0,889 plus 1,333, and I'm getting, you see, I'm getting 2,222. So this is equal to 2,222, meaning I am correct in that sense. So that is one way you could have dealt with this question. The other one works on proportion, and I hope you'll be able to use proportion properly in this case. Let me show you what I mean by saying the other method works on proportion. If you are using it, you just need to be a little bit careful. Now, what you must understand, we said resistance and current are inversely proportional, or when the resistance is high, the current is low. Now, you expect in the 6 ohm resistor low current because it's 6, but in the 4 ohm resistor you expect a high current comparing the two. So if I say 6 ohm current is small, but in a 4 ohm the current is high. Why? Because current and resistance are inversely proportional. When the resistance is small, the current is high. When the current is high, the resistance is small. Remember, resistance is the resistance to the flow of current. Now, using that information, I can use in this case ratio. So these ratios are 6:4. Now let me find the total ratio. So first is total ratio, which is equal to 6 plus 4 equal to 10. So I'm going to then look at the first one, which is divided like that, which is 6/10 times, remember they are splitting the current, and the current was 2,22. So 2,222. It will give me the answer there to say 6/10 times 2,222. It will give me an answer of 1,333. See that answer? It is 1,333 amps. I do the same thing here. 4/10 times 2,222. This is proportion. When you're using this one, it's based on proportion. 4/10 times 2,222. The original current, it is 0,888, which is 0,889. So this is equal to 0,889. Now look at this. This is amps. Now you will always get those two answers. Remember, we also did get 1,333, which was passing, but we saw that 1,33 was passing through the smaller one, which was here. And then the actual answer, remember, we got the current through that was 0,889. So now, how do you, whenever, let's say you didn't know the first method, how do you work on this? You start to remind yourself of how resistance and current are involved. So you see, we used 6, but we got high current. We used 4, but we get small current. But what you need to do is to interchange them like this, so that the I4 is linked to R4. In this case, I4 must be linked to R4, or not. Let me not just confuse here. I'm saying here, when you interchange, what you're saying is this current comes here, which is for 0,889, and this current comes here, which is 1,338. So in reality, the 1,33A is the one that is flowing through the 4 ohms. 0,889 is the one that is flowing through the 6 ohms. If you know the relationship between inversely or indirectly proportional, then you can conclude and say, therefore, I passing through the 6 ohm resistor is 0,889. Just need you to be more practice on it, and you'll be able to flow with that. As I said, guys, this was a total of how many marks? 13 marks for those circuits, and the total mark allocation was 100 marks, and this marks the end of this paper. So I've done the first section, question 1 to 3, which is part 1, and then question 4 to 6, which is part 2, and question 7 to 9. Now I would like to apologize for the second part, which is question 4 to 6. There was poor sound quality, and I will say just bear with us. I think the equipment is the one that was in a way behaving that day, but I hope you'll be able to understand. We have come to the end of our lesson. I hope this was of benefit to you. Remember to subscribe to our channel, share the channel with others, as sharing is caring, so that they can also benefit. And remember, these are 24-minute lessons, meaning if the video is more than 24 minutes, I will encourage you to study these in pockets of 24 minutes. Why? Because your mind can absorb up to, or can concentrate up to, a maximum of 24 minutes or even less. So anything you do after, you will be understanding, but you are not understanding at the optimal function of your mind. So I'll encourage you, don't strain yourself unnecessarily, and you sit 2 hours watching this video. After 24 minutes, you'll be just wasting more time, because what you could have done was to break it into 24 minutes. You take a break, go outside, do something totally different. Do something, take a walk, play some soccer, play some football, just go and chat with friends. I know people say I'll go on my phone, but sometimes the phone even strains. It's better to have a dialogue with someone. Go out, just do something for 5-10 minutes, and then come back again and continue from where you left for the next 24 minutes. Again, take a small break, do something totally different. Make yourself a cup of coffee, make yourself some juice, totally different. Look for someone who can just share a joke with you, and then come back again for the next 24 minutes. You keep on doing that, you will benefit from your studies. Guys, we've come to the end of our lesson. Thank you.